Hi everyone, this is Zihan from IEEE Lab at Stanford. Today I will talk about our work on confidence transfer across using adversarial networks, which can be particularly helpful when learning from suboptimal demonstrations. When you think about learning tasks such as playing basketball by imitation, it would be wonderful to try to learn from optimal expert demonstrations, like LeBron James. But in practice, we don't always have access to that type of data. Instead, we have access to suboptimal playing data. For example, how our best friend in middle school was playing basketball. Even then, we end up using these demonstrations and learning from them. Similarly, we would like our robots to have the ability to learn from imperfect suboptimal demonstrations. It becomes a problem for imitation learning, how to learn from both optimal and suboptimal demonstrators. Imagine a robot arm with a Rubik's Cube. We would like the robot to put the Rubik's Cube on a certain position on the shelf shown here. Depending on the expertise of the demonstrator, there could be demonstrations with different levels of optimality. Here are some suboptimal ones. For example, these demonstrations would put the cube in a wrong spot. Here are some OK ones. The demonstrations put the cube at the right location but take a detour leading to a longer trajectory compared to the optimal solution. Here is the optimal one. The green trajectory puts the cube at the right location following the shortest path. So in order to be able to learn from all these different demonstrations with varying level of optimality, ideally, we would like to have a confidence predictor that can tell us how much we should trust in each demonstration. For example, a confidence predictor can provide a value between 0 and 1, and as an example can assign a low value of 0.13 to the suboptimal demonstration. When the optimality of the demonstration increases, the confidence score also increases. And finally, the optimal demonstrations will be assigned a score of 1 or close to 1. Then, by having these confidence scores, we can train an off-the-shelf imitation learning algorithm when the demonstrations are reweighted based on the confidence value from the confidence predictor. However, you might wonder where the confidence predictor comes from. One idea is to learn a confidence predictor from annotated state action confidence pairs in a supervised fashion. You might find out that confidence labels are required in this process. These confidence labels may come from different ways. It can be human annotated, normalized rewards from some known environment, and so on. And yes, as all you imagined, the annotation of the confidence score is time-consuming and requires a lot of effort. So instead, imagine that you have a simpler environment like a four-legged ant, and you can have your confidence measures in this environment. Our key insight is that a confidence predictor in this environment can potentially transfer to a new environment, such as a five-legged ant, or from a robot in simulation with disabled or damaged joints to a real robot. By observing the robots, we can find some sets of robots that they have different dynamics but have the same goal and probably share a similar confidence predictor. Then let's get back to the problem. Can we transfer confidence predictor with little or even without labels? This is the problem we want to tackle. Consider we have two robot environments, source environment and target environment. Source environment has tremendous label data and target environment only has few or even without label data. Our method has 3 steps. In the first step, we train a confidence predictor in source environment using collected demonstrations. The confidence predictor, which is a neural network, has 2 parts, a source encoder and a decoder. In the second step, we use a generative adversarial network to transfer the source encoder of the confidence predictor by using unpaired data from both source environment and target environment. Let's take a closer look at the second step. Here is the basic version of the model. We first use the trained source encoder to encode the states from the source environment. Similarly, we encode the states in the target environment by using a newly initialized encoder, which is also a neural network. Then, the discriminator is to distinguish if the encoded state is from the source or target. We use a minimax scan loss to train the target encoder and discriminator jointly. The basic model works. However, it suffers from various problems. One issue is compounding error due to state misalignment. Since robot trajectories are temporal, a misalignment in current state could affect future alignments and further cause problematic training issues for the target encoder. In order to make better state alignments, both temporally and distribution-wise, we design additional features on the basic model. Our first improvement is called multi-lens partial trajectory matching. In the basic model, we only use discriminator for single states. Rather than using a single discriminator, we use multiple discriminators to capture the trajectory-wise matching in the latent space. It preserves the temporal relationship between consecutive states and actions, and makes the latent features of state-action pairs more likely to be aligned with respect to the confidence. Besides matching temporally, we also want to match the distribution of states between source and target. In the basic model, only the distribution of features outputted by the encoders have been matched. However, this feature-level matching might not be enough. The distribution of confidence scores could also provide useful information to guide the training of the model. Here, come to our second improvement. Our second improvement is by using both feature level and confidence level matching to guide the model training process. Feature level matching happens after the data passes the encoders. And the confidence level matching is to match the distributions of final confidence outputs. These two levels of alignments provide enough regularization for the model to be properly trained. By combining both improvements and adding up the losses, we have the final version of the model, which looks like this. In the third step, we fine-tune the target confidence predictor by using the few examples, and then we use the confidence predictor to infer the confidence scores in the target environment. Here are some experimental results by using our model. We have three sets of results: Mujuku, Franca Panda robot in simulation, and real Franca Panda robot. In Mujuku, we did experiments in Richer and Ant. In the Richer setup, our source environment is one joint Richer, and our target environment is two joint Richer. Our baseline is scale. Here are the animations for the target environment transfer. As you can see, the Gale method fails to reach the target point. Our method follows a similar trajectory as Oracle and achieves the goal. Here are the results for Ant. The Gale method runs to the right with a longer distance, or turn around at the starting point. Our method moves to the right smoothly and reaches a similar performance as Oracle. In our experiment, we also compared with another baseline, dynamic cycle consistency. As you can see, our method outperforms both Gale and DCC and gets a similar performance as Oracle. Let's go to the simulated Franca Panda experiments. Here are the experiments on the simulated Franca Panda robot. The task is for the robot to reach the middle of the circular bed. The source environment is 7 degrees of freedom robot arm, and the target environment is 5 degrees of freedom. Optimal timeout means we only use optimal data and timeout data to train the robot. Similarly, the other one is that we only use optimal, suboptimal, and collision data to train the robot. In the first setup, Gale moves very slowly and is very far from the target point when the execution ends. DCC is similar. Ours can move with a fast manner and reach to the point close to the target. Similar to the second setup. We also did experiments in real panda robot. Here are the experiments for the real panda robot. The task is to put the Rubik's Cube in the empty place on the top half of the shelf. The source environment is the 7-degree freedom panda robot in simulation, and the target environment is the same one in real. As shown by the video, by using Gale, the robot fails to reach the target location. Our method can successfully reach the target location on the shelf. It has a similar performance as Oracle. Here are some key takeaways. We demonstrate that by transferring confidence predictors from one domain to another using confidence adversarial transfer, we can effectively learn from suboptimal demonstrations. Thanks for coming to our presentation.